Hi, my name is Jiaxin Hu, and I'm glad to present our paper, Learning Multiple Network via Supervised Tensor Decomposition. The motivation of our paper is twofold. First, the scientific studies, such as neuroimaging and social network analysis, often collect the tensor observations with set information. Second, the tensor observations may consist of non-Gaussian measurements, such as binary and count data. Figure 1 gives us an example in the brain connectivity network study. The left-hand side is the tensor observation composed by the binary adjacent matrix from n individuals. And the right-hand side is the feature matrix contains the individuals and information, including their age, gender, and other features. Our goal is to identify the structural variation in the data tensor affected by the set information. To achieve our goal, we propose our supervised tensor decomposition model. We let Y denote the order K tensor observation, let Xi's denote the feature matrix contain the set information for each mode, and let the multiplication symbol subscribed by I denote the tensor by matrix product on the ith mode. Our model is presented in the equation 1. On the right-hand side, the f is the non-link function depending on the data type in Y. C is an unknown full rank core tensor, and MIs are unknown factor matrix consisting of orthonormal columns. Figure 2 illustrates our model for an order 3 tensor. The left-hand side is the mean of the data tensor. In the right-hand side, the three-colored matrix x1, x2, x3 are feature matrix. The Y tensor C and the Y matrix M1, M2, M3 in the dashed rectangle is the tensor decomposition under the supervision of the site information. The features Xi's affect the distribution of the tensor entrance through the matrix product Xi Mi, and the factor matrix Mi's not only reduce the dimension in the tensor decomposition, but also reduce the dimension of the feature matrix. We call Mi's as the dimension reduction matrix, and we call the matrix products Xi Mi as the supervised tensor factors, or sufficient features. The core tensor C collects the interaction effects between the sufficient features. The unknown parameter consists of k plus 1 blocks, C, M1 to Mk. To estimate the unknown parameters, we first propose a likelihood-based estimator which satisfies the equation 2, and then we propose an alternating optimization algorithm which updates one block of parameters at a time to solve the estimator 2. Figure 3 shows the likelihood trajectories when we apply our algorithm to the normal data tensor with different settings. We can see that our algorithm converges quickly in few iterations, and the objective values at the convergence points are close to or larger than the values at the true parameters. This implies that our algorithm can give high-quality estimations. We also find statistical guarantees for our estimator. Under mild technical assumptions, with high probability, we have inequality 3, which is an upper bound for the angle distance between the column spaces of the true MI and the estimated MI. We also have the inequality 4, which is an upper bound for the Frobenius norm between the true supervised tensor decomposition and the estimated decomposition. Last, we apply our method to the brain connectivity networks from the Human Connectome project. Figure 4 shows the top brain edges with large effects. Red edges represent the positive effects, and the blue edges represent the negative effects. Subfigure A shows the global connectivity pattern. We can see that the nodes within each hemisphere are more densely connected with each other. Subfigure B shows the female effect to the connection. We can see that the female brains display higher interhemispherical connectivity. Subfigure C and D show the effects from the age 22 and age 31 respectively. We can find that several edges in the frontal probe region have declined connections in the group of age 31. Our results are in agreement with other neuroscience studies. This implies that our model is able to highlight the brain connection variation with biological meanings. More information about our data and codes are available in our R package. Thank you for watching.